Welcome to the tutorial for ASketch, a tool for sketching alloy models. In this video, we will show how to use ASketch by stepping over its command line interface, which is provided through the bash script also named ASketch. To use our tool, there are three main inputs to be created: a partial alloy model, a generator, and a test suite. Before running the tool, we will illustrate each of these inputs. On the top left-hand side of the screen, we have a partial alloy model of a singly linked list, and we want to create a predicate acyclic, which ensures the list will not have cycles. In this example, we have created the high-level structures of our model, namely signatures list and node. However, for our predicate acyclic, rather than try and formulate the acyclicity property ourselves, we instead provide a sketch. The sketch contains one quantifier hole, two compare operator holes, and two expression holes. We will show how to use ASketch to fill in these low-level details and complete this predicate. For all of our example models deployed with our tool, we have one expected solution commented out. This enables users to check if solutions produced by ASketch are equivalent to the expected solution. On the bottom left-hand side of the screen, we have an example generator for our model. This provides a guide for generating candidate fragments for each unique hole in the sketch. For instance, the first line requires the quantifier hole to take one of three values, either all, some, or no. For expression holes, regular expressions are used to outline the generator. On the right-hand side of the screen, we have an AUnit Test suite. The AUnit Test suite captures both the behavior acyclic is intended to express and the behavior acyclic is intended to prevent. For instance, we can take a closer look at the first two tests. Test 0 states that an empty list should satisfy the acyclic predicate, while test 1 states that a list with one node containing a self loop should violate the acyclic predicate. With these inputs created, we are now ready to use ASketch. The first step is to build the tool. This is done by running the -- build option for the script. If successful, you will be alerted by the output of the command. Then we are ready to run ASketch and try to find a completed version of our acyclic predicate. To do this, we use the -- run option of the script and provide the necessary arguments. The first argument is the location of a partial alloy model with holes. The second argument is the location of a generator, which is used to produce candidate fragments for the holes. The third argument is the test file, which contains an AUnit Test suite that captures the expected behavior of the model. Then there are two optional arguments. First, you can choose to specify a scope. If you do not, a default scope of 3 is used. Lastly, you can specify how many solutions ASketch should report. If you do not, a default value of 1 is used. We have chosen to run ASketch with its default scope, but we want to take a look at the first 10 solutions. When we run the command, ASketch will start its execution and will display logging information to the user as it executes. First, ASketch will report the interpreted candidate fragments for each hole provided by the generator. As you can see, the expression hole's regular expression generator has been expanded out into concrete alloy expressions. Then, ASketch provides general information for each hole in the sketch, as well as the entire search space of the sketching problem. This search space is computed by multiplying the size of all the individual search spaces for all holes. Lastly, ASketch reports the solutions found, if any, as well as the solving time for each solution. For our command, we asked for the first 10 solutions, but ASketch only reported 8. This is because the number of solutions to report is treated as an upper bound, and for our linked list example, these 8 solutions are the only valid solutions to the sketch. All 8 of these solutions are semantically equivalent to each other, and solution 6 exactly matches our expected solution.